Okay. So the camera is here, right? Luis, where's the camera?
The camera is here.
Is that good?
Yeah.
Okay. So good morning, everybody. Today is our second day. We're still in a kind of a review mode of things that you should know. We're going to get to the beef of it and halfway through the day today when we're going to cover cohort study, because this is really the type of observational design that we need to use in natural experiments at time. So we're going to talk a little bit deeper into that. But in a refreshment type of perspective, reviewing things for you like we did it today, I want to point to this lecture here, Measurement, Error, and Causation. We're not going to cover it today because of interest of time. Error types of error sources control. But this is a very important lecture that I prepared for you. I want you to study it, to read it. Everything is there. Trust me, everything that matters. And it can be applicable to any kind of studies. Okay? So this is a very rich, I'm going very quickly so you can see there's a lot of material. I want you to review it in your own time. The folks here at University are going to release those lectures. They've been released already, Fred?
Not the release, not the material, just the texts. But I'll give them the material today.
Okay. Yeah, he's promised to release everything, the whole course today. So you're all going to have access to this lecture as well as all the other material, including the reading material I want you to read. There's a sequence there. You can see it. Okay, so this is an important lecture we're not going to cover here. It's a review again for you who should have studied that at some point in it. Now we're going to start reviewing the study design. That's the beef of our program. Although the first hour today is going to be about kind of studies that we don't usually use to evaluate interventions, but it's necessary that you have a kind of firm understanding. It's a little bit of a review also. So we're going to start by covering very quickly correlations and cross-sectional studies. As you know, there's a sequence of epidemiological designs. And these sequences is very important for you to feel strong as you're going deeper into more complex design. Make no mistake, a randomized clinical trial is extremely complex design. It can be made very complex. It can be the simplest studies possible, with the simplest statistic possible, but also can be very complicated. We're going to see that tomorrow, okay, in all different forms of clinical trials. But today we're going to review the basics of descriptive and kind of a semi-quasi-analytical epidemiology design. So again, just to remind you the kind of a general perspective on the study design. You have this grand scheme that you can design based on whether we assign exposure or not. So if the scientist, you and me, assign exposures to a treatment or to an intervention or to a risk factor to groups, we are into the so-called experimental side of things. If you do not assign, you are in the observational side of things, meaning you're observing things already happening. When Sir Don Hill studied the relationship between tobacco and cardiovascular disease, tobacco and lung cancer, tobacco and COPD, they did not say, hey, doctors in England, start smoking. He just said, hey, these guys are smoking for a long time. Let's observe and see if they die. That's what they did. It's called observational design. On the other hand, if you assign exposure, you have the power to assign exposure to exposing an individual to tobacco or not, then you are in experimental design. By the way, question to you, why would nobody in the 40s or 50s or 60s or even today experimentally assign tobacco to a group and do not assign tobacco in another group? Think about it. At any rate, so you have the experimental side and the observational side. The two lectures today, early now, in the next 45 to 50 minutes, we're going to cover two separate sections on correlations and cross-sectional studies. Those two types of studies are in the observational family. Later on today, we're going to cover another observational family of studies, which is the cohort study design and a little bit of the case control. Okay, so that's the day today. After that, you're going to do into a more experimental, and there are two types of general experimental: the experimental, truly experimental studies, in which you not only control the exposure, but you also control whether you randomize the study or not. You assign the exposure based on either a random algorithm or you not. And that's the experimental, true experiments, control trials, and the non-control or quasi-experimental type of studies. Okay, you're going to learn that these two studies are very important to evaluate intervention. They are the two main ways to evaluate intervention effectiveness: experimental designs and quasi-experimental designs. And we're going to learn here, how do we make a quasi-experimental design as close as possible to an experimental design to eliminate biases. And that's what the early lecture that I mentioned today. Study that lecture about biases: misclassification bias, selection bias in its different forms, confounding, and variation of the two themes, okay? As you can see, I wrote here on the side ecological correlation design as a kind of a important aspect, because sometimes is the early stage of learning about something that could be related to an intervention and to the effect of intervention. Sometimes it's almost correlational. You're going to see that as a quasi-experiment called interrupted time series or discontinuity design, regression discontinuity design. By the way, the observational design, one used to evaluate an intervention effectiveness, is what we call a natural experiment. You're not controlling too much things that are happening. You're just an observer that takes advantage of it. That's observational. But sometimes you're also an observer, but there is a quasi-experiment going on. You did not participate in the initial phase of the quasi-experiment, but there is a quasi-experiment. Let's say the city of São Paulo, the Department of Health of São Paulo, decide to intervene in 5 major neighborhoods of São Paulo, 5 suburbs of São Paulo, with a new school health program. But they didn't have money to go everywhere else. Boom, 5 neighborhoods with that program. Well, they create a natural experiment, a quasi-experiment, because it's not randomized. They are offering a exposure to an intervention to 5 neighborhoods. And then every other neighborhood in São Paulo, the remaining in the city of São Paulo, are the control group. That's a quasi-experiment. You're observing that. That's a natural experiment also, okay? So natural experiment is either cohort or case controls. You're taking advantage of exposures happening by itself, or somebody actually intervene in a way that you can take advantage and create a quasi-experiment, but it's a natural experiment because you did not create that. The circumstance created the experiment. Before we even get started into the real lecture, one of you asked me yesterday, that was my first question, the only one so far, how do I make a difference between efficacy study and effectiveness study? Okay? And I say, depends. It depends on the context. I'm going to give you 2 examples. One context is about innovation. It's about novelty, something that never happened before. So if something never happened before in terms of exposure to a treatment or to an intervention, expose a group of people or one individual, 2 individuals, 20 or 100 or thousands to want something, and then keep somebody else as your control, okay? If that study was never done for a specific intervention and for the relationship between that intervention and a specific health outcome, let's say cardiovascular health, and a new treatment for cardiovascular health, or a new intervention in a community for cardiovascular health, it was never studied before, then it's an efficacy trial, especially if this trial is done with the rigor of a randomized design. So you really have an efficacy. It's the first time that you learn about that, and you're controlling a lot of the elements. So the efficacy is very much associated with novelty, something new, innovative, and that you don't know, you don't have the knowledge yet, and the fact that you are controlling is really experimental, and you're controlling in a good way. You have randomization, you have blindness, you have a clean people participate, you don't have much loss of your follow-up. You're going to learn that a little bit more again. Once you have those elements, you are dealing with an efficacy trial. Okay, we're going to see that very clearly in treatment of medication, like a medication and a specific health outcome in clinical trials.
And you're supposed to have an ideal situation of compliance. Everybody's taking the drug.
Excellent. Luis Ramos has mentioned the fact that also you have perfect compliance, so close to perfection in compliance. And therefore, everybody's taking the drug you recommend as part of your treatment. Yeah. So that makes this very controlled circumstance or context a efficacy trial. You're going to learn that when you do clinical trial. You're going to see more clearly that. But I'm trying to extrapolate as to context beyond the clinical design, which is about clinical populations of patients and treatment of medication. I'm talking about interventions in public health, population health interventions in general. Even there, if you have a lot of rigor in your design and you have control on a lot of elements, and it's the first time you're evaluating that measure of efficacy or effectiveness, you want to call it, it can't be called effectiveness. It has to be an efficacy because it's well controlled and it's not reality. Once you go from that well-controlled study and you disseminate that study everywhere, and you try to evaluate in the real world with all the problems you have, that's an effectiveness trial. We're going to see that more and more as we go along, okay? So let's start. We're going to talk about correlation, but let's start here. Simple example, it's in this paper. Fatalities associated with farm tractors. In 1982, the number of farm tractor-associated deaths was described in terms of time, place, and person by using record from existing public health surveillance systems in the U.S. Well, you're dealing here with person, place, and time, traditional descriptive epidemiology, okay? And you can come up with something like that. Fatalities associated with farm tractors, and it was published in Public Health Report. I forgot which state or if it's the whole U.S., but I think it was a specific state over a period of time. You see the death here on the y-axis, and you see the hours where the accidents occur on the x-axis. So you see a.m. means in the morning, p.m. means in the afternoon. And you can see here, where is the peak of the death? The peak of the death is around mid-afternoon, okay? The lowest, before the lowest death is at about 12 o'clock because everybody's eating. It's lunchtime, right? So it's only 5 deaths. But right before lunch, you see the peak. It goes up very high. And then at the very end, between 4 and 5 o'clock, what happening here is people are very tired. Okay? They're becoming ready to go. And here it's going down because very few people were still working. So it's actually, I'm not looking at rates here. Remember, I'm looking at the actual counts of death. So if I happen to look into a rate, if the people leaving from work, it wouldn't matter because I'm talking about the denominator is changing, the rate will change proportionally. Or the rate, let's say the rate is stable, but the denominator is changing. But here what you see is the effect of not only tiredness, hunger, but also the decreasing number of workers in the field. After 4 or 5 o'clock, very few people are working at night on the farms, but some people do.
Yeah, but the rate could be high because the 2 working at 10 p.m. can be only the 2 and be 100%.
That's what I'm saying. I'm not looking at rate. I'm looking at counts. I can explain this whole thing with these 3 things: hunger, tiredness, and number of people working in the field. Okay, it changed over time. So this is called descriptive statistics. Here again, the same fatalities. Look at age groups. So what is the age group more affected by death? Is the very old, right? Or close to old. Okay, so it goes up with age. Okay, but it's greater in the 60, 69. That's acuity, is the dexterity.
0 to 9 overrun by the tractor.
0 to 9 is because people work, get their kids in the fields in the U.S. at a very early age. It's not, there's no 0, but there might be some 7 or 8 years because you break down in bigger age groups. So it's probably 8, 9, 10 years older who are working in the field, and they are going to cause an accident. They should not be working, too young for that, but they are working, and that's why you get an accident. But here's also the aging issue. A person gets a little bit older, their eyesight goes down and things like that. Also, the location actually was in Missouri. I should remember. Yeah, that's where that state I lived for many years. Fatality associated farm tractor. You can see what the most of them happen in the northern part of the state. That's a colder part of the state. There's a lot of icing in here because the conditions. It gets as cold as north of Canada and Alaska here in this point. Okay. Can you use this information to determine what caused death? Can we use it? That's a question to you. You can conjecture like I did. It's descriptive epidemiology. You're almost certain, but you're never 100% certain exactly what caused the death. You can only generate hypotheses why the death is occurring. You cannot prove or disprove or have evidence in favor or against it. That's too strong. So what study design could answer these questions? That's the gist of this whole course. You're going to learn what you need to use to evaluate how to reduce this. So what's causing it? Okay, we're going to learn today about case control cohort. Could answer the question, what's causing it? Easily on the fatalities associated with tractor, driving a tractor for agricultural work in America, in Missouri. So conducting studies, you attempt to find associations between things. That's the main purpose of study, association between a risk factor, tobacco, and the evolution and development of lung cancer over the years. So it's a fair question to answer, and was answered in 1952 by a cohort study. Okay, so we're going to show that. Again, the famous breakdown, simplified even further, of the epi studies, the experimental, the observation. In the observation, you have descriptive. We just gave you one descriptive. It's surveillance-based: person, place, and time, and allows you already to make conjectures why, to hypothesize why these things are occurring. You almost certainly know a little bit why it's occurring, but you can never be sure. Maybe there's a third or fourth or fifth element that's also helping to cause this interacting. You don't know. You need a study design to elucidate this. So in the grand classification of the traditional epi, I'm not including the experimental part, just the observational design here. The easiest and simplest form of design is a case report, a case series. Case report, I want to have one case, but it's so unusual that I publish it because it's the first time people ever seen. So the first Kaposi cancer case in a young person was reported in the US. People had no idea there was HIV or AIDS or anything related to sexual, but they reported as a Kaposi sarcoma in a young man. They didn't even know there was associated with homosexuality at that point. Today is not, but back then, make no mistake, the epidemic is associated with the homosexual behavior. It was associated initially. So it was a case report. And then later on, a colleague of mine who happened to be Dr. Curran became the dean of the School of Medicine, started investigating that deeper in HIV. Dean of Emory University School of Public Health for many, many years. Great, brilliant mind from CDC. But the early cases are own case reporting case series. Then after that, you have a cross-sectional in which you take a sample. We're going to see that later in a few hours. And the ecologicals is comes there with the cross-sectional. It's the first level. So what we saw before with the tractors associated death is a little bit of ecological and not. You have the counts, you know where they're coming from, but it's like, I'm going to show you what it is in a few seconds. And after that level of descriptive epi, you can make analytical inference. You can hypothesize, but it's not a high analytical study because you cannot test it with that design. You're just observing things, it's observation and descriptive. Okay? You have no basis to make an assessment statistically whether that thing is caused by what. Okay? Whereas analytic, you actually make those connections. So I'm going to skip that. You can read it. I've been beating about the bush about this issue. Again, more ways of looking at more. I'm going to skip case report. Okay, I gave you that case report of HIV. I'm going to give you a little bit of one. Novel coronavirus cases with a 55-year-old individual from Hubei province in China they may have been the first person to have contracted COVID-19, the disease caused by the new coronavirus spreading across the globe. At that point, when that doctor published that, he had no idea that was going to be the biggest epidemic over the past 15 years. But it was a case report. And after a colleague of mine from CDC, after reading this, called me, we talked about it and say, my God, this might be something created in China. By January 2 of 2020, 41 admitted hospital patients had been identified as having a lab-confirmed 2019 nCoV infection. Because at that point, they already had found a way to use the DNA and create a new test already in China for that. So they could do a first series. They did a case, then a case series.
This was 2020,
Yeah, to 2020. Yeah, 2020. The first case was actually in 2019, December 19. This first case, 55-year-old. It was published in a blog. It was not published in any journal. And the guy who published, I think the Chinese guy made sure he disappeared. He died later on in prison. Example of case report: 5 young, previously healthy homosexual men. I mentioned to you this with Spinoza, Carini, or Kaposi. Actually, I got confused. Kaposi was also published as a case series. The Pneumocystis carini is the one that was published as a case first report. But you can read that. You can see there are many examples. Even some other areas like angiosarcoma, the liver, and associated with vinyl chloride later on. But it was reported as three workers initially. Okay? 3 workers. Not a study, a design that was complex or anything like that. So that's what descriptive stat does. There's a special kind of type of descriptive statistics that I want you to give you some sense of it, which is the correlational design. Why? Because you get into some of the statistics that later on you need to use it when you're doing time-interrupted time series. So it's basically correlation coefficients and linear regression. So the genesis of that in epidemiology came mostly from correlational design. So they study to correlate the rates of disease with specific characteristics based on aggregated data from the whole population, as opposed to an individual level analysis. I don't have one person at a time. I just have a rate for a region, or for a city, or for a suburb, or for a school, a whole rate, meaning 500 people, 5 developed the disease out of 500, so I have 1 in 1,000 here, right? That's a rate. So, and then I have rates like that for 10 other counties, and I'm comparing their rates. That's an ecological analysis, a correlation analysis, okay? Because I'm not individually seeing. We're going to see an example of that. So example, colon cancer rates and milk consumption per capita. When I study really deep in epidemiology, one of the first things I did is to study colorectal cancer, because I've done a correlation study between meat consumption in 1985 and colorectal cancer. And my correlation analysis showed that countries that eat lots of meat had a lot of colorectal cancer. So I thought maybe there's an association. Like me, many other doctors did the same thing. I thought I was innovative. People are thinking like me. There are a lot of people doing that. So later on, I had a chance to study at Emory University, and my thesis was the relationship between colorectal cancer and meat consumption, protein intake, so to speak. But that time, it was a cohort study, something different. So I had a chance now to do something more design, analytical design. But the first hands I put on this issue was a correlation analysis. I got the rates country by country, the incidence rate of cancer, new cases out of those who are at risk to become a case, multiply their percent times, get their denominator to calculate the incidence density, right? And I had that incidence density for every country in Europe and Western world. And then I look at their incidence rate of colorectal cancer coming from their national registries of cancer. And guess what? There was a correlation there. It turned out in a big cohort that I did later on, I couldn't find any relationship whatsoever. Okay, it was confounded by many things. That's why it shows in a correlation. But it gives you the genesis of something. For instance, the relationship between COVID-19 and hydroxychloroquine became evident for a lot of people through correlation studies, good correlation study, which did not get disseminated because the media had already made a decision that chloroquine was a bad thing. Okay? So it was politicized, something that should not be. Hydroxychloroquine is one of the safest medication. I use it for 10 years. Never seen, I was training cardiology, never seen a patient ever develop arrhythmia. And I'll give it 2-3 times the dosage. Being a doctor, primary care doctor in Recife, where 30% of the population goes back and forth between the Amazon region and Northeast, because they're all migrant Northeastern, who left the Northeast of Brazil and went to Amazon and back and forth. Lots of malaria I treat. Never seen an arrhythmia. And I did have electrocardiogram in my little primary care clinic for 10 years. At any rate,
You're not treating COVID at that time, right?
no, I'm talking about the safety of hydroxychloroquine was questioned. So correlation studies can be completed quickly and inexpensively, used to generate etiological hypotheses, not to test hypotheses. Cannot be used to test any hypothesis because you don't have what it takes. I'm going to show you why. Inappropriate conclusions regarding exposure-disease relationship. I gave you the example of colorectal cancer and meat consumption. If you do a correlation or ecological type of studies like this, you're going to find relationships. It doesn't mean they exist because something called ecological fallacy. Okay? Example here, relationship between alcohol and coronary heart disease and mortality. Okay? Alcohol to coronary heart disease and mortality. Implications for public health policy. You can see on the left axis per capita alcohol consumption per liter. Okay? And at the bottom, you can see the death rate for coronary heart disease in 1972 for males 55 to 64, very specific age group. Why? That's the age group where most of coronary heart events happen and the fatal ones happen. So you have a good reason to test this relationship. And you can see here that the people who do the highest consumption, France, Italy, Portugal, Spain, they have possibly one of the lowest death rates for coronary heart disease, where people have very low consumption in Europe. This is Western and civilized world, so-called.
But they were looking at any alcohol or wine
Alcohol overall. Alcohol overall. So what you see here is a negative relationship. As the alcohol intake goes up, the death rate goes down. Alcohol goes up, rate goes down. Alcohol goes down, rates, what happened? Goes up. Okay? So is that true relationship? Later on was proven to be somewhat true. But it's now we know well, we're studying well with cohort studies, a U-shaped curve. Alcohol is very good in small amounts, especially wine, more than anything else, to protect from a coronary heart event, okay? Especially one that's fatal. However, if you start drinking a little bit too much, goes beyond 2 drinks of wine.
because the champions on alcohol consumption all drink wine, right?
They do. That's another thing that's hidden here. It's just alcohol overall. But the correlation, it was the first time people said, well, maybe there's something there. Maybe alcohol is protective against death associated with coronary heart disease. And it was. It's proven now, very beyond doubt, in my opinion. Again, not experimental design, even though the studies later on or cohort study, analytical epidemiological design, they're still observational, prone to biases. And that's why I want you to study the first lecture I mentioned earlier today. Okay? So measure the strength and direction of the relationship, like the analytical design, but it's not analytical. And there are 3 main measures there. We're going to cover one well, and the other ones I wanted to study. Okay? We're going to cover the first measure, Pearson's correlation coefficient, because it's automatically provided to you once you do other studies later on. You're going to learn a more complex one. You can extract that even from an Excel program and don't need to go fancy with Stata or SAS or anything like the R. You can get actually from Excel a good correlation, a good linear regression, a multivariate linear regression too. So that's why I wanted to mention that type of descriptive, kind of observational and hypothesis generated study, because it allows you to come up with these statistics. Correlation does not imply causation. Remember that. You heard that somewhere else. it shows only the two things are related: tobacco and lung cancer. In this example, I gave it to you today: meat consumption and colorectal cancer, alcohol intake, and death due to coronary heart disease. So it only shows the correlation, association, but you cannot prove or have strong evidence that this relationship is causal. Causal relationship means I extinguish every possibility of other things being explaining what my outcome is after some time. And I couldn't find it. Therefore, I accept to be causal. You can never prove or disprove statistically anything. You can just raise the level of evidence to kind of negate a hypothesis. And that's why I have no hypothesis, which is called kind of a hypothesis that nothing is happening here, and the alternative hypothesis, something is happening here, either direction or no direction. There's another lecture tomorrow I'm going to mention. Maybe I'll have time to show it to you about that issue. Okay, it's very important for the experimental design because you're really in a territory of statistical testing. So lack of correlation does not mean independent. Relationship would be more complicated than what the correlation measures. And therefore, the correlation is just the first level of understanding of the relationship. So what is the Pearson correlation? It's a coefficient. It's a mathematical measure, or statistic in this case, that allows you to measure the linear association between two continuous variables. Okay? So they may be related in a nonlinear. If they are related strongly but nonlinear, your Pearson is not going to be an important test. It's going to be non-significant. You're going to learn that the other two tests, Kendall and Spearman, can do that for you. So you should try all three. But more than that, before you even do the correlation, I want to show it to you, you do a graphic display of your relationships. So that gives you a clue whether this relationship is linear or not. You may see a curve linear. Forget about doing a Pearson on that. You can see something dispersing with a variance open up. It's completely different animal. Don't do Pearson. But anyhow, so to establish a relationship, you know what is missing here is the graphics. Where? Oh God, I put the graphics after. Sorry, folks. Let's go back to the graphic. Quickly here. If I could trace a line here, you could see that if I could trace a straight line coming right through Portugal, from the top here on the left, all the way to the bottom at about 1,200 for the number of deaths. Okay, so if I could trace a straight line here, you reflect pretty much the average distance from all the points in this graph. So if I trace a line that's a straight line from left to right, from top to down, okay, top, bottom, left to right. I don't know if you're seeing my cursor, but probably not, but it's going like this. It could be a line that minimizes the distance between every point in the line, okay? So that linear relationship generates the correlation coefficient you're talking about, okay? So the correlation coefficient in this case is a Pearson correlation, and this is the formula. You can see that's all about distance from the mean. The summation of the x's, in this case, that example, that the x is alcohol, right? That's your exposure, your exposure variable. And y is your outcome. That's your death due to coronary heart disease. So you can see that the summation of the product of the two differences from the mean, okay? That's what the correlation is, and the variance of those differences, which is a product of two individual variances. It's very simple to understand what a correlation is. You basically say, hey, this thing are strongly related. And if they can be strongly related in a negative way, like this one, meaning the more alcohol I have, the less death I have. So the highest consumption of alcohol here is France, which is about close to 20 liters of alcohol per year per capita. Okay, and the death is around 200, whereas the lowest alcohol consumption is actually Japan. But forget it, Japan's an outlier here. You have Finland here is lower, and then the death is very high. Japan's an outlier because Japan have very low alcohol consumption and very low death. So that should be a tail. If you eliminate Japan, from this curve, you can see the straight line is perfectly aligned with most of the data points. Okay? So that's what your correlation is. This is an important measure that establishes the relationship. Sample covariance divided by 2 sample standard deviation. That's what it is. So the summation on the top is your covariance, basically. And the bottom is your 2 sample standard deviation, the square root of the square of the difference from the mean. The product of the square of the difference from the mean. So that's what the correlation is the sample, that you have a sample of the truth, covariance on the top, divided by 2 sample standard deviation. So that's what it correlates the two things. So it can be a positive or negative value. It can go from -1 to 1. -1 meaning the relationship is very negative, meaning the more I have of this exposure to this factor, the less I have of the outcome. That's a negative relationship. Whereas a positive relationship, the more I have of some bad things, the more bad things happen. Okay? And that's your positive correlation. So the example we saw, which is coming from top down, left, right, that's a negative correlation. It should be close to 0.75 there, because Japan was an outlier. If I eliminated Japan, it would be 0.9, that correlation, as close to -1 as possible. It's -0.9, that correlation for alcohol and coronary heart disease death. Negative value means that one variable increases, the other decreases, experience and time to code the medical record. That's a study I did in our hospital there. So there's a strong negative correlation. The more experience and time a person had to do the coding in a medical record, the better they become, and they shorten their time to do the medical record coding. Pearson correlation, plus or minus, points fall perfectly on a straight line, does not indicate the slope other than direction. No linear, zero. So perfect -1 or perfect +1 means the points fall perfectly in a straight line. There's no covariance at all. So that's what the red line is here. Okay? That means it's a perfect correlation, positive correlation in this case. If it happen to be the line from this line that you see here, the red line is from left to right, bottom up. So it's going straight up. That's a straight, perfect positive correlation. The inverse of that would be a straight line, like an X crossing this red line. Okay, from bottom up, from top, bottom, left to right. You don't see, I didn't draw that. There's another one, which is 0.1x, which is a line that's as close to 0 as possible, meaning there's no linear relationship. So all the points fall around the point 0 of the correlation. It's a non-linear relationship. And you have something like, you can have 0 correlation when there's actually a correlation. You can see here, this is a curvilinear relationship, which is a square. The y is the x square. So it's a quadratic relationship. So there's a true relationship, but your Pearson correlation is going to be 0, because Pearson can only detect straight linear relationships, right? Here, there's so many data points, which is at the bottom, so many data points to the top, to the left, so many data points to the top, to the right. So the Pearson doesn't know if this thing is going bottom up or up, bottom, left to right, or right to left. They have no idea. So it's like, for Pearson, it's going to be a straight line on the 0 correlation type of cut. So descriptive stats, a little bit more Pearson's example of negative correlation. I showed it before. There's another one here is going from left to right a little bit. It's a slight negative correlation. A slight positive correlation. This is the length of stay in a hospital and the total charges. You should know that, right? The more you stay in a hospital, the more expensive it becomes. So you can see that it's a straight line up, but a little bit of an S curve here. That's an interesting stuff. Here is the calculation of that length of stay I did for these data points that you see here. Okay, you see those 5 data points? I calculated loss of staying and the charges, how much it costs for each patient. Patient 1, patient 2, patient 3, every one of them have a different length of stay. Okay, and then I have the calculation, the X means. You see how that's calculated? You can actually do it by hand. and you can see how these numbers come about. So I give you a true example, and you can use data analysis to pack stat plus in Excel to do that. And type Corel, and put your variable 1, variable 2, common, variable 2, and Excel is going to give you this value. But I'm doing by hand here so you can see how that's calculated. Okay? Just apply the formula straightforward. What I did is I programmed the Excel sheet so that D does the covariance, the product of the two covariance. And then the E and F, they do the two part of the product of the variance, the standard deviation, actually, with square root of the individual variance. Okay? So you just can program, you can easily program in Excel to do this. I'm not going to cover Spearman, but think about it. There's other relationships, monotonic relationship, linear relationship is a special case, and so on and so forth. Okay? I'm going to skip that. I want you to start. I gave you an example in Excel. You can do that. See how I did it, the loss of stay, rank. So that's how I program it to do the calculation. Okay, Spearman, Kendall, read that. The other correlation coefficient for nonlinear relationships between an exposure to a potential risk factor or a potential interventional factor and the outcome, which is a health outcome, because you're in health, you're interested in health outcome. Okay? So emphasis in correlation, you can use a statistical test. You can use the Pearson and say, okay, is this Pearson correlation coefficient significant? That's another question. There can be a small Pearson correlation, 0.1 or 0.9 or 1, a perfect 1, negative or positive. But are they significant? Because that's another question. Is statistics, or could it have happened by chance alone? That's big value of the correlation. So you have a statistical test, which is a t-test for the correlation. You take your Pearson value, you multiply by the RN in the data points that I show there in of the countries. You have about 30 data points there. So it's 30 minus 2, 1 divided by square root of 1 minus R squared, which is your correlation square. Okay? So that's your formula for your statistical test with the 2 degrees of freedom, because it's n minus 2 is your 2 degrees of freedom, and a test statistic. It's a t-test. Remember the t-test table? You go to a t-distribution, and then you find your p-values there. Okay? So you can test with the hypothesis test. I say R, which is Pearson correlation in this case, is equal to 0, meaning there's no relationship. It's a straight line, a horizontal line, and the relationship between the y and the y-axis and the x and the x-axis. Okay? So I say there's no relationship between alcohol consumption and coronary heart disease death. That's my Pearson statistic. And then I go and I set, after I said that, I said, well, I alternatively like to say that R is going to be different than 0. There is some relationship. I didn't specify what kind of relationship, just there is some relationship. That's your alternative hypothesis, okay? And or I could have said, no, I think the relationship exists and is positive. I would have written R is greater than 0. That's a directional hypothesis testing, okay? Which we're not going to get into that. There's a lecture tomorrow. I'm going to give you an overview, and I want you to study that lecture. I'm going to send a note to all of you with Fred today, say, read this thing before tomorrow's lecture, because this stuff, statistical test, is going to be even more important. I'm just going to give you a little preview here. A preview, just a taste of it, okay? After you state your hypothesis, your alternative hypothesis, you set acceptable alpha level. That's your chance of making a type 1 error. I'm saying to myself, if I make a type 1 error, I want to make a type 1 error 5 out of 100 times or less, not more than that. And that's a standard in science over the past 100 years. It's a totally, there's no rule in that. It's just an accepted standard. Okay. So you know what type 1 error is, right? Type 1, type 2 error. Type 1 error is when you say, hey, there's a relationship here, when actually this relationship does not exist. It's your bad statistic, your fake information that's causing you to believe something doesn't exist. That's the type of error in epidemiology that we're trying to avoid like hell. It's like, you know, showing the crucifix to a vampire. So you don't want to do that. Type 2 error is different. Is when there is a relationship, but your statistical testing, your design was not powerful enough to show that relationship. You lack power in your statistical analysis, and therefore you miss to find a true relationship. You can make that mistake 20 out of 100 times, and people still accept that, or 10 out of 100 times. But they would not accept making a mistake of saying, hey, there's a relationship here between meat and something, when the relationship does not exist. So again, once you test statistics, you saw how I found that value before, right? You plug those numbers in here. The 0.93 is your correlation. We found out for LOS, length of stay, and charges. And you do 5 minus 2, 1 minus 0.93 square. That's your R square, right? You take the square root of those two quantities, multiply by 0.93, which is the correlation. You end up with a test statistic of 4.45. What's the magic number in a Z distribution that you find an alpha 0.05? That's 1.96, right? So if you square that you got a chi-square statistic. The t-test is different. It's neither Z or T. You have to go and look at the table of t-statistic. But I guarantee you this number is going to be close to significant or a little bit under the significant level. I think. Yes, it is. Use the t-distribution for alpha level. Your t value is actually at 3.18. So your number is greater than that. So if your number is greater than that t, then you say this is not only a interesting correlation, it's very high, 0.93, but is statistically significant. It actually exists. It's a strong correlation. If you had a number that was different, you reject the no sense, you have the right number here, so you can reject the null hypothesis. So after you do the comparison, say t statistic greater than 18, because it is greater, I conclude the null hypothesis, there's no association between length of stay and charges, cost of the medical care. It's wrong. I cannot accept that. So I conclude the alternative is true. There is a relationship. Again, Kendall, you can do that. But more importantly, you do correlation in a territory of linear regression. You are linearly associating, like I show you, the linear relationships allow us to calculate a correlation. You can read about it because I want to really move quickly to something else. But the linear relationship is important you understand. Review, please, linear regression. And from that point on, review multivariate regression. And after you do that, you feel good again about both linear and multivariate regression. Then review other types of multivariate regression that's not linear, okay? Including categorical regression. That's what you're going to be in the territory studying tomorrow. There will be a lot of that, especially on the not so-called experimental design or in the cluster design we're going to talk about tomorrow. Read about it. Again, it's nothing more than a linear relationship between your Y health outcome and your X variable, whatever is your X. Okay? This is typical positive correlation. Here you have total fertility rate and infant mortality rate per 1,000 live birth. So countries with a high infant mortality seem to have high total fertility rate as well. This is back in the 80s and 70s. I'm still truthful. For most countries, they are in this stage of development. Most Western world and rich countries are past this time 100 years back, 150 years back. So they're not in that situation. But this is an interesting, you can explain that to some extent, right? The more death you have and higher fertility rate. So what comes first? The total infant mortality rate or the total infant infertility rate? What do you think? Fred, what do you think comes first? So the graph is showing countries with high infant mortality rate have high total fertility rate. This is a correlation analysis. Again, it's a linear regression. I'm going to show how that is calculated. But it's basically saying, hey, the more death I have in my family, the more kids I'm going to create because I'm agricultural. These poor countries in Africa, in Asia, and some Latin American countries, and back in the 70s and 80s, are mostly non-industrialized, non-service oriented, more agriculture oriented, and agricultural families need lots of hands. The more kids you have, the richer you are. Because more death, absolutely. But it's like one feeds into the other. Okay? So you have a little bit of, here one is a strong positive correlation. That means a straight linear line going from left to right, from bottom up. The straight line almost crossing to the middle of the two axes. And then you have a less positive, but still positive, but you have more spread of the numbers. Still a straight line from bottom up, from left to right. Again, a little bit stronger. See, this is 0.5 correlation. This is 0.9 correlation. It's very, almost line up on a straight line. Perfectly negative correlation. A 0.5 negative correlation. A 0.9 negative correlation. Left to right, but this time around, from top to bottom. No correlation whatsoever. Okay, the points don't explain any relationship between X and Y. There's no pattern except a straight horizontal line. That will be the line that minimizes the distance from each point to the average of all points. It's a straight horizontal line, so it's zero correlation. And you can interpret that not only with the correlation coefficient, but you can actually create a regression. What's the advantage of having, in addition to the correlation coefficient, a regression, a linear regression? It allows you to create predictions. You can say if these two things are related, it tells how they are related. It doesn't, the correlation coefficient just say they are related, strongly related or not. The linear regression say they are strongly related or not, and they are related in this way. As I move this way to the left, I go up this much. That's what it's saying. So here you have the classic, weight equals minus 114.3 plus 106.5 height in meters. So weight in kilogram and height in meters. So the first number here, that's your B0 in a linear regression. I don't have time to refresh you in a linear regression, but that's your linear coefficient. That's your value for Y, which is the weight, when X is equal to 0. It's like the average of all weights. That's your B0 plus B1 or beta 1, which is the coefficient for height. And height is the X. So B1X. Okay? So the height change, the weight change for every unit of change in height. Remember that? That's your derivative. Remember your algebra, folks? Remember your algebra? The slope of the curve, rise and runs, remember? So that's what it is. So linear regression is very important. And you're going to remember that because you're going to look into multivariate regression when you're dealing with regression discontinuity designs and time series analysis later on. And I can't, in this short course, so few days to do it, cover all the material. But I wish I would be here. Luis, next time you bring it for 3 weeks, and then we can do the basic review of all these basic stats so you can go to advanced, apply to the epidemiological matter. And I'll ask one of our statisticians here to help me with the lecture. I'm no statistician, folks. I'm just curious about numbers. But that's an important concept for you to remember. So here, I'm basically saying this is the relationship. My beta 1 is 106, okay? And I can test whether this beta 1 is significantly different from a beta 1 that means nothing, being 0, right? A beta 1 of 0. That's your T value here in the regression, linear regression, spit it out from an R analysis of 9.21, and the alpha level set as 0.05. You got something even smaller than a 0.05. 0.000 goes on because this number is way big. Okay? So that's your t-statistic testing for the coefficient slope, for the null hypothesis coefficient for the X height is equal to 0. It's not equal to 0, it's 106. So that's the unit of change in weight for every unit of change in X. So every time we move height, go from 0 to 1 meter to 2 meters, I change 106 kilogram in in weight. That's what they're saying in this regression here. Okay? P-value for each term, test the null hypothesis that the coefficient is equal to 0. I already mentioned this to you. Here are the values. That's another correlation. I brought another example. You can read about it. What time is it, Fred? 10? Okay, we're going to quickly read this stuff, review that. We're going to quickly cover a very basic, still in an observation, still in the descriptive, but it can be looked at analytically like the correlation, but it's the cross-sectional study. In 15 minutes, I'm going to give you the gist of it. So cross-sectional, it's just a study to describe things. It's a survey. Every time you have a random sample survey, any type of random sample, simple random sample, cluster random sample, stratified random sample, cluster stratified random sample, okay? Every time you have any modification, a 2-stage, 3-stage random sample, 3-stage cluster stratified random sample, every time you have a random sample of things and you use that sample to describe that thing that you're interested in, that's a cross-sectional study, folks. If I take a random sample of the 70 chairs here, okay, I take a 10% random sample, that's a 7 out of 70 chairs here, and I say I'm looking for defective chairs, and I evaluate and see how much defect I have in the chairs here. I'm doing a random sample, and I'm trying to identify a factor called defective chair in here. I can do the same thing with people. I can look at my clinics and my hospital, and I do an exit interview, a random sample of people who just went off. They left the physician's office, and they're about to leave, and say, "Ma'am, do you mind giving me an interview you randomly selected to be part of a little study? It's going to help the clinic, it's going to help your health in the long run." Most people accept that, 90%. So you have a decent random sample with very few refusals. So it's a very valid type of random sample. We're going to look into that. That's a random sample. If I go and randomly select, randomize in a random way, randomly select houses in the Villa Clementino around the Unifest campus, okay? I know where the house is. I can go to the city hall here and obtain information about the house addresses, and I do this for study. I have an IRB, an ethical review board, say it's acceptable, and I random sample 1,000 houses out of 10,000 homes here, okay? When I random sample those 1,000 homes, I have a survey of the homes and my interest in finding out how many of those people are age 65 and above. And then if they are, I ask the question, can you bathe yourself? Can you take care of your cleaning yourself? Can you cook for yourself? Can you eat alone? Do you need any help with anything? That's what Dr. Ramos does in the Center for Aging Studies here, okay? That's a random sample of the population. And I do a survey, and I do a cross-sectional study. So I explain what a cross-sectional study is. We can finish the lecture now. No, I'll go a little bit more. So the way you present cross-sectional studies, you really prevalence estimate. You learned that yesterday. What is a prevalence measure? It's a measure of things that exist, whereas incidence in epidemiology is always new things that's happening over time, whereas prevalence is what you have at that moment, new and old things. They are, and therefore you identify them to a random sample. So I'm looking to the random sample of women in the state of Missouri compared to national and year 2000 goals for the state of Missouri back in 1995. I'm looking at a random sample of adult women in Missouri, and I asked the simple question, have you ever had a pap smear, which is a Papa Nicolau test to detect cervical cancer? As you know, it's one of the cheapest screening tests ever created, and highly sensitive and specific. So you have both high specificity and sensitivity, which is not focus of our lecture, but it's something very important in epidemiology too, clinical epidemiology, that is. And that's the cross-sectional study of pap smear is. You take the women, sample them, and we call them in their home. It's a random telephone interview. And we ask them, have you ever had a pap smear? Yes or no? Here you have it. You present it like that. You have the prevalence of pap smear in Missouri is the blue, the so-called blue color, that's lighter blue. And year 2000, that's the goal. That's where we want to go. Is the darker, I'm nearly black, but it's really dark blue. And the red is the national level of women that ever had a Pap smear. Or in this case, actually, I misstated. It's having had a Pap smear within a year and within 3 years. Past 3 years and the past year. Sorry. But anyhow, you can see that here is 67.5% of the women in Missouri at that point in time in 1995 had a Pap smear within the previous 12 months. And about 85% had had it with 3 years. That's pretty good. That means these people are protected against cervical cancer, which is the easiest of cancer to treat if I detect at the cervix. If they spread out in the uterus, I'm in a different territory. You have Krukenberg tumor. It's going to go all the way through the intestine to the pancreas and name it in the bones. So here you have a simple way to detect. You do a sample survey of the population and say, hey, my public health program are in good shape. My dissemination, health promotion of screening and offering of screening is pretty good. Okay, that's what the cross-sectional survey does for you. Usually that's descriptive of the design. Eligible people are randomly sampled at a point in time or over a short period of time, and the outcomes and risk factors are measured at the same time, whatever you're interested in. Okay? So you see that? The yellow that's blank is because this is for different design. I'm going to show you case control cohort. These other little boxes are all filled out. But in a cross-section, you only have one group. But ineligible or not, participate or not, and then you go and measure exposed to this, or that, this type of health outcomes on this. It's all collected at the same time. That's another characteristic of a cross-sectional or survey. Every measurement is done at the same point in time. So you can never say, oh, I found a lot of people in the survey, they have a high rate of obesity. And they are the same people doing everything right. They're eating a lot of fruits and vegetables. They're eating all the right stuff. They're exercising every day. And they're all obese. So, my goodness, exercising and eating well cause obesity. That's what you conclude. No, dummy. What happened is that after 40 years of health promotion about physical activity and nutrition, it's actually people are thinking about, at least those who are obese, they're doing the right thing because they went to the doctor said, you need to change your diet. You need to exercise. And they are exercising. A little bit too late. Here, you have all measured at the same time. You don't know what comes first. You don't know if the physical activity and the fruits and vegetable eating is coming after they become obese or before they become obese. We know from cohort studies and from experiments that's the inverse, meaning they became obese and then start doing the right thing. And that's why I found a relationship that's positive when it should be a negative relationship. Okay? So cross-section has this problem of trying to use a descriptive statistic to estimate an analytical mindset, trying to understand what is related to what. Okay? Same thing with correlation. It's even worse, correlation coefficients. So you can hypothesize like I did here, but I'll warn you, don't do that if you can. But I did, and I'm going to show an example at the end of this course that I use a natural experiment that I use cross-sectional studies. So I'm defeating my own message to you. Please don't use cross-sectional or surveys to do analytical work, but I'm going to show you an example, a crazy one, that it's remotely possible given some circumstances. Okay, here's how you would go analytically about it. There's very important two measures I want to show to you that you can extract from cross-section. One is the prevalence rate, like you know it, and the rate of two prevalence. You can say smoking people and non-smoking people, and you look into some other factors, and you calculate the prevalence for the smokers and the prevalence for non-smokers, and you do the prevalence of one group divided by the prevalence of the other group. It's called prevalence ratio, which is different than a prevalence odds ratio. You can also do a prevalence odds ratio if you present your data like that. Let's say I look at the obesity and the eating of 5 or more fruits and vegetables a day. I can describe like that. Like if I'm looking at a cohort study or I'm looking at a case control. But remember, it's not a cohort, it's not a case control. All these measure, the exposure and the outcome, the disease, all measure at the same time. So I don't know if one comes before the other in time. I don't know what caused the other. That's the key question. But I can find a correlation between them. And this is how you do it, to prevalence odds ratios or prevalence ratios. And they're calculated different. They are related. They're cousins, but they are different, folks. Pay attention how they're calculated. Okay? The prevalence ratio, A, B, C, D, you see that? A plus B or A plus C divided by A plus B, C plus D. That's the total. Whereas the odds ratio is a little different. A divided by B and so on and so forth. Like here. You see that? A multiplied by D, like the traditional odds ratio. I want to show you that later today. I want you to pay attention to that. I gave you some formulas, and I show examples of how to calculate using these formulas for the confidence interval around the prevalence estimate or a confidence interval around the prevalence ratio or prevalence differences. Okay? Again, more formulas for you. So you have a lot of information to read about it. I didn't want to detain much time on cross-sectional correlation. That's why I gave you in 1 hour and 15 minutes. You can read about it. I'm going to give you a break for about 10, maximum 15 minutes, folks. We need to cover good material on cohort studies and case control because they can be used for natural experiments. Remember, this whole course is to take you to what I'm taking you now, and more importantly, tomorrow and then Tuesday, which is the intervention design, the stronger intervention design, stronger than natural experiments. Okay? So, see you in 10 minutes. Então, pessoal, back to English. This course is supposed to be taught in English. We'll keep going. If you have any question, you need not to ask your question in English. You can ask in Portuguese. Send an email to me. You have access to my email address. Fred, do they have my email address?
No.
Please provide them. How can they ask me questions? Yesterday I was asking them to ask me questions.
We are here.
I know, but that means live questions, okay. But sometimes people have questions later.
Okay.
So send them my email as soon as possible so
Okay.
they can answer questions. So now we're back. We basically finished the review, the basic reviews about things. And some of that review I could not cover totally on the lecture, but I gave you lectures. You can study them. And the lecture early in the morning that I did not cover, it's about biases in epidemiological study. Please read that lecture. It's very important. Also, the very first lecture we gave it, the foundation of statistical foundation of epi methods. I want you to read it and study it. There's a lot of good examples, a lot of my drafty notes from the past. And tomorrow I'm going to give you another one of those that I'm going to just touch it on statistical tests, but I'm not going to cover that. It's a statistical lecture, actually. But I prepared it for you. So these are the 3 reviews which are not covered as a lecture by me, but I want you to study them, please. And I'll send a message today, again, to remind about those lectures. Fred's going to make available to you all the lectures. I should have done that yesterday. For some reason, we miscommunicated and you did not have all the lectures yet. But today, every lecture is going to be given to you, okay? So let's focus on cohort studies and measure of associations. And remember, the first day yesterday, we talked about measures of occurrence in epidemiology. More important measure of all, the incidence, 2 types of incidence, cumulative incidence or risk, which is another name, and the incidence density or incidence rate, the true rate. And we also cover very, tangentially, prevalence, but it's very simple. We understand what a prevalence is. So these are the fundamental measures. There's something else called odds, but it only makes sense as you see it today in case control when we're doing as a measure of association, the odds ratio, the ratio of 2 odds. I did mention that in the statistical foundation lecture that I want you to study. There is an explanation what the odds is. Odds of exposure, odds of outcome, or odds of disease is the same thing as odds of outcome. And then how you create a ratio of 2 odds and becomes the odds ratio, okay? So study that. So cohort is the first and fundamentally more important observational design. So in here, you're going to learn about the relative risk or risk ratio, which is another name, which is a measure of association. It measures the strength of the association between a risk factor or an intervention or a treatment or a factor with an outcome. The outcome be it a disease, be it a healthy status, be a healthy behavior, whatever. And then you also have other measures called absolute risk, which is the risk difference, and attributable risk, which I'm just going to mention because it's not the focus of this study here. We also gave it to you information about biases early on today. Did not cover the lecture, but I want you to study. It's a beautiful lecture. I think it's one of the most structured lectures I created for you, okay? It has almost everything about biases in epidemiological studies. So we're going to learn about the cohort, its characteristics, what the risk factor is, and how to measure the association between factors and outcomes. Factors being a risk factor or a treatment. We're in a territory of analytic epidemiology, still observational designs. Still on the right-hand side, if I'm looking at that graph, if I am the graph, is my left-hand side, the no, I cannot assign exposure and observation design. I'm observing things that are happening. And I gave you one study already, cross-sectional to you, and another one, the ecological study. I'm going to give you one more today, now, and later on, another one. I'm going to give you cohort now and case control in an hour and 15 minutes from now. So in a cohort, subjects are categorized on the basis of their exposure to one or more risk factors. So exposed to factor A, B, or C, or exposed to a factor that has 3 levels, A, B, C, or 1, 2, 3. Okay, smoking, heavy smokers, not so heavy smoker, and light smokers, and non-smoker. You can classify it like that, 4 level. Follow-up, people to estimate disease rate or risk. So goal is to trace or follow up cohort members over time and to identify among those who are exposed to the risk factor, how many develop the condition I'm interested in. Among those unexposed, how many develop. And once I have those 2 numbers, I do a ratio of the 2, and I create a ratio of 2 things, right? That's your risk ratio or relative risk or incidence rate ratio. Okay? There are 3 measures there, actually 2 measures, but one of the measures, relative risk, is also called risk ratio. It's the same thing. Every time I say relative risk or risk ratio, I'm talking about the same thing. It's the cumulative incidence in one group divided by the cumulative incidence in another group. Whenever I say incidence rate ratio, I'm talking about really a rate ratio, the ratio of 2 rates. And the rate is the incidence rate, which has a denominator that has a dimension of time. Person time is the denominator. So determinant or risk factors measure in pre-selected cohorts because I need to be sure that they have the factors ahead of time. The factor that I'm interested in studying has to precede the existence of the outcome. I don't select people based on whether they are diseased or not, because let's say I'm interested in cardiovascular disease. So I go about finding people out there who do not have cardiovascular disease. And then I say, I'm interested in the relationship between tobacco and cardiovascular health. That's what Sir Daw and Hill did in 1948, 1950s. So they say, hey, I'm interested in this relationship. Let me find a group of people I can follow up. And that group of people, it's easy to trace them. And I have a lot of information about that. That's the physicians. And he was a physician in England. All of them since the 1800s have perfect records when they become a physician, when they become ill and don't work for more than a few weeks or months, and when they die. It's all recorded there. So you say, hey, I'm interested in the relationship between cardiovascular health and tobacco. I'm going to ask these guys how many smoke. So he went about setting up a study in which to determine these people who are not diseased. The registry tells if they're diseased or not. And they are not dead, they're alive, they're still practicing medicine. Okay? So that's good. Now I'm saying, do you smoke? He asked the simple question, do you smoke? Yes or no? What do you smoke? Pipe, cigar, cigarettes, what else? And then if they smoke, they ask the question, how many cigarettes do you smoke? How many cigars smoke a day? And how many pipes you smoke a day? How often do you smoke a day? I don't know how exactly he was phrasing the words. And then he said, for how long have you been smoking? When did you initiate smoking? 3 or 4 questions. That was the whole study. I'm not kidding you. But he had all the information about their age, their gender, their specialty, they're all physicians, their income. They had a lot of information about them. And he followed them over time. That's a cohort study. Question, Luis, do you have any point?
Yeah, in case of smoking, probably should ask if you ever smoke, because the guy might have stopped yesterday.
Yeah, good point. I don't know if you heard what he said. He probably asked the question, did you ever smoke first, like as an opening question? Because the person didn't no longer smoke, he would be a smoker that stopped smoking, an ever smoker, okay? But don't smoke anymore. That's a category. Let's say if you're doing a categorization of smokers versus non-smoker, you have smokers, former smokers, and never smokers. You see that? You create a gradient. That's very important. You're going to learn that later on. Good point, Luis, and well said. The health. So then over time, you go out and follow them up, and every year you tally them. You check, are you still alive? Because there's interest in death. And what kind of death? The record shows in England very perfectly if you die of a coronary heart disease or not. So that's how they did their study. At the end of the study period, the results are compared. How many of the smokers died of a heart disease? How many of the non-smokers died of heart disease? And found a huge gradient. Among the smokers, the gradient was like 3 times more than the never smokers. So he found a great, same thing with lung cancer. He started with cardiovascular, he went to lung cancer and published the most important paper today about lung cancer and smoking. He found gradients between 2 and 17, depending how much you smoke and how long you're smoking. Meaning, if you're a smoker and heavy smoker for 20, 30 years, you are nearly 15 times more likely to develop lung cancer than non-smoker, versus those who only smoke a few things a day. So that's how you set up your study. Again, it's a prospective look into exposed and unexposed groups over time. And then you follow them over time, measure them. And I gave you advice to you yesterday. I'm giving you again. Do not wait for too long. Try, if your study has a 3-year study, measure them every 6 months at least. Because something happened in 6 months. It's a long time for health. If you study chronic disease, a lot can happen in older people in 6 months. It's a lifetime of things happening. So you have to measure constantly to know if they're changing the status. If you cannot measure constantly, then you measure a long period of time. You need to make some assumption. If the person disappear from that cohort, you're following 100 people and you lost 30 people in a cohort, you give them at least half of the cohort time. 1 year, I lost them somewhere between January and December. I say most of them were here until July. I make that assumption. I may be wrong for one person, but I may be right on average. That's what you expect. Some people left in April, some people left in November. So they cancel each other, and therefore you give them 6 months. But if you can, it's better not to do that. So measure them every 6 months, because then you know how much person time they contribute. Remember how the incidence rate is calculated? You need person time. So if your incidence rate are based on a person time, every 2 years you measure. I lost them for follow-up. You lost a great number of your people. It's possible in a cohort study. And you have to give them an incidence rate calculation. It's going to be very off maybe, because you say, oh, they gave at least 1 year. In 3 years, they gave. I make the assumption, but it may be wrong. Maybe most of them left within the first 6 months of your study. And then you're giving them too much time, person time. You dilute the incidence rate for this group. And you don't know what happened to them. You don't know what the outcome is. So again, measure more frequently in a cohort study if you can. Cohort study is designed to compare incidence rates of exposed and unexposed groups of people. In a cohort, again, you did not give them the exposure. They already exposed. They're the one that made the decision. Back in 1948 or 1930, any doctor in England smoking was a smart person, actually. It was debonair, was very healthy. I can show it to you. The public health department of most states in the United States promotes smoking as a healthy thing. I have their health promotion posters in the Missouri Department of Health. I bought them and put over there. 1938, 1945, 1947. Then the smoking study from Sir Darwin Hill came. Things changed from 1980. By 1964, the Surgeon General of the United States published official notes saying the federal government of the United States condemns smoking because it causes heart disease and causes lung cancer. And things start changing. And then 30 years later, we have laws that basically make it very difficult for people to smoke. And almost you don't see smoke anywhere in America. Still a lot in France, for instance, or Italy, but not in America. The whole generation is being born without ever seeing a room. Yeah, so, exactly. For our cohorts, back then, the GI Bill to help people to go to war and when they come back and they have money. But also before that, there was a pre-bill that say the soldiers in the Pacific and Europe, the American soldier, every one of them, it's a decision of the federal government. We receive a pack of cigarettes a week and a bar of chocolate every week. No matter where they are, we're going to reach them and give them. That's true. Okay? So, yeah. So actually, there was a lot of whiskey involved in that. Patton, this infantry group always had whiskey for the soldiers. But anyhow, this is how ignorant we were about tobacco. A cohort study found out that you can't do that anymore. So here you define eligibility criteria to be in the study. okay, ineligible, eligible. You basically, if you're going to study something that only happen after age 70 or 65 or 80, you're not going to include young people because you're going to wait 80 years for that event to happen, right? If you're interested in death due to coronary heart disease, are you going to include 18 years older? No. So you make them ineligible to maximize what you're trying to understand. But sometimes you also make ineligible people whose characteristics may compromise the quality of the study in terms of absence of bias, like difficult confound to control. If you can eliminate them by an ineligibility criteria, you do so too. If you study infectious disease, also you're going to eliminate making eligible people have immunity because they already had the disease early that confer lifetime immunity. So there's a lot of eligibility, ineligibility issues. And then you're going to go about study their level of exposure. Sorry, for some reason it disappeared from my, I don't know what happened here, Fred, but it's supposed to be exposed and unexposed, participate, not participate, okay? So for each group, the exposed and unexposed, that's what you really, the study start. You then, after you define that they are eligible for your study, then you get exposed and unexposed people. And then out of the exposed people, you say how many participate, how many don't. That's not your decision. The ineligibility is your decision as a researcher, okay? And you invite them to be exposed and unexposed to participate. If they decide to not participate, it's their decision, it's not yours. You can only invite them. But you want to make sure that you have a convincing argument and a beneficial argument so that people can participate in your study. Usually in the studies involving clinical settings, we offer clinical diagnostic tests, which are usually necessary for your study anyway, but you give them as a benefit, you elaborate on that so to convince them to be in your study. You need no randomization here. You need no random sample of anything. You just invite people. You know they don't have the outcome you're interested yet, and you want to know if they are exposed. You want to just invite them because of exposure. They have the exposure, and you invite some others who don't have the exposure. Sometimes you know by knowledge of lots of factors that in a whole community, you're going to get exposed and exposed people. So you don't worry too much about, I need to find X exposed and unexposed. You go about like the study Dr. Roman does. It takes the whole Clementino village as my population. Okay, you have 10, 15,000 people, and you go after it, trying to say, I'm going to recruit 4,000 people to my study. Okay, and I know I'm going to get exposed to this and then exposed to that. I'm not worried about that. I have enough people here. I know the prevalence of smoking in São Paulo is 20%. Therefore, if I invite 4,000 people, I'm going to get 800 people here, smokers, and 3,200 people, non-smokers. Okay, so that's how you do. And you invite them to be in your study and create your cohort. And out of that, you want them to participate. Once they participate, I didn't put over here, but when they are participants in your study, that you start following them up over time, some of them may be lost, may lose. You may lose them because they may leave the study. You want to make the study so enticing for them, they don't leave your study. And by measuring them close in time, it allows them to see that your team is close to them. You're offering diagnostic tests every 6 months. That's a good thing. It costs me something. And even if I have health insurance, it may cost me the extra there, but you're doing the effort for me. I can even go in your home and take your blood. Oh, that's a good thing. So again, you want to make them participant. You don't want to lose them to follow up. And then also when they're in your study, you follow them up over time. You measure your outcome of interest, yes or no in both groups, the exposed and unexposed. Sorry for the word this came out when I transfer the graph in a new thing. It disappeared. I don't know how. So usually you present the cohort study like that. The exposed group, row-wise or column-wise, could be, I could reverse that. It wouldn't make no difference. As long as you know what your denominator is. Your denominator is the exposed and unexposed group. A plus B, we also call N1. And C plus D here in this graph, we call N2. Okay? So that's your denominator of the exposed group and denominator of the unexposed group for your calculation of the risk, because I'm presenting A, B, C, D counts. the actual number of people going in each cell. If I want to present you as a density table, you would have only counts for the top, the exposed group, okay? And you have another row that's just the density, the actual number of your person years. And here on the total, okay, you have person years. Sorry, not the row, it's the column here. The total column here, you wouldn't have A plus B and C plus D. You have A plus D, A plus B, and T1 and T2. Okay, T1 for the follow-up time for the exposed, and T2 for the unexposed. Okay, it's a little different table. I'll show that later on to you. But then you display your cases of your outcomes by the exposure nature of your cohort. There's another issue, because I said that you follow people over time. So it's always prospective. Cohorts are always prospective. You have a group of exposed, unexposed. They're all at risk for developing the disease. They don't have the disease. Therefore, they are all at risk for developing the disease. Okay? And you tally the disease over time. That's your prospective in nature. But you can also implement the design as a retrospective study. You have your population at risk, and you look back at the exposure. Look back at the exposure. The exposure have to have happened in the past, but you are able to look back. That's your retrospective cohort. The nature of the relationship is still prospective. You are guaranteed that the exposure precedes the disease in time. You know that. You have data to do that. Okay? But the disease is measured ahead in terms of time. You measure the exposure in the past, but you have certainty of that exposed and unexposed group, but you measure the disease as it occurs. You're still following people up. And both the exposed and unexposed and the outcomes could have occurred in the past. It could have occurred right in the past, but you have the data to replicate the prospective nature of their relationship. You follow that? I hope so. So retrospective can still enumerate with certainty the number of exposed and unexposed to be followed up. Okay? So you go through records and find out that people were there. In the case of Dr. Ramos' study of the Clementino village twice, he had follow-up studies. That's a real perspective, not only the nature's perspective of the whole cohort, but he collected data prospectively. He established a cohort of exposed and unexposed group to various factors, various risk factors. So he could do many cohorts, studies out of one big cohort, and follow them up over time and found the disease over time. He actually measured prospectively too. But if he had done that data, and I have a completely different design, a different exposure, he didn't think about it, but it's there in his data set, it's already collected. I'm doing a retrospective study myself. I did not collect and follow these people up. He did. But I'm using his data to do a retrospective cohort. It's a kind of a secondary data analysis, one possibility. But sometimes I have records of the exposure in the past, and I'm still observing the development of the outcome over time. But I have a record of the exposure in the past. I go after that, and I establish exposure in the past. So the prospective cohort, disease-free, exposed and unexposed, are followed up over time to look how many develop the disease over time. In the historical, I have disease-free, still disease-free, exposed and unexposed population, followed up prior to the initiation of the study to measure incidence over time. I still have the same thing. It's just how I implement them is historical or retrospective. Okay, so this is another graphic, kind of a presentation of it. You can look it over. Criteria for defining exposed group. This is very important. They should represent a homogeneous group from the population that gave rise to the exposed and unexposed group. Okay? And you also want to measure something that has high frequency of exposure. When Dr. Ramos select a random sample, because he wanted to do it, it need not to be a random sample, of 4,000 adults from the Villa Clementino of some age, okay? He was hoping to have most of the exposed group there, and he is right. It's a large segment of the population. Population he understands well. There's a lot of information about this population in São Paulo, and you can find out they have. But you may have some exposure you may be interested. That's very sparse in this group that he collected. That's not going to be good for establishing a cohort for that exposure. Let's say he's interested in a risk factor that may affect the dependency of that older person to be dependent or not of others, okay? And that factor is very rare in this group. He won't be able to study it because it doesn't have enough in or the power in your study to do the analysis. So you want to make sure that you have the relative high frequency of the exposure you're interested. Luckily for him, in a large cohort like that, from a segment of the population, most of the things interested, the frequency of the exposure is high for most factors. So he can study them with no loss of power in your study. You're going to learn that tomorrow about power and stuff like that. You want to minimize loss to follow-up, because loss to follow-up diminishes the power of your study, but also introduce selection bias. Okay, selection bias is the study is biased by the manner in which you select people in the group or not. Study that lecture I mentioned to you before. Many sources of exposed cohorts, you can study them. Most famous one in America for many, many years is being the Framingham study, in which the city of Framingham is a cohort. Like Dr. Ramos did here with Clementino, it's a whole neighborhood. It's like a mini village. It is a village. They have a whole city there, Framingham, a city of maybe 200,000 people, but being followed up for 60 years now, more, maybe 65 years, something like that. Okay? There's also a famous one in Tecumseh. I think I forgot what state. And in Iowa, there are 3 counties, Iowa. I think there are many famous cohorts. I list a few of those big studies. Criteria for defining unexposed. They also should represent a homogeneous group of the same population where the cohort exposed came from. You cannot take exposed and unexposed from different population groups that come from different sources. They should come from the same population. An exposed subject from all the similar population of the general population, that's the whole point. You need to, ideally should come from the same village, same city, in all walks of life. So they represent both an exposed and exposed people. And minimal loss to follow-up in the unexposed group too. Both loss to follow-ups will cause bias in your study and loss of power. Source for identify exposures, where you go after the information for exposure. Pre-existing, if you're doing a retrospective cohort, you can look at birth certificate, medical records, employment records, and so on and so forth. You can see the list here. I'm not going to go over that. You study that. Oh, God, again, the names are disappearing, Fred, when I put in this new.
Okay, I feel this.
I don't know how. Sorry, folks. But anyhow, you got your Ellis, but this is a real study done, I believe, in St. Louis by my dear friend of mine, Terry Leaked. I hope I have the source there. If not, I'll send it to you later on. Okay. I think he was interested in deep chest wound infection following a CABG, which is open heart surgery to bypass your coronary so that your ischemic heart disease will improve. Okay. So that surgery may cause deep chest infection. And he had the idea, just look at correlation data actually from the hospital, that the obese people appears to have a higher rate of the infection post a CABG surgery. So he designed that cohort study, and he had obese patients, non-obese patients, followed them over time. Didn't have to wait too long because they're obese, but the event of their interest, the CABG, they all went through CABG. Participant, not participant, you have the CABG, and follow the CABG, which is the surgery, open heart surgery, then in a few days or hours, you're going to see if they have deep chest wound infection or not. Okay. So the goal is to trace a follow-up cohort member independently of exposure. That's another important thing. You should find a way to design your study that your exposure, your follow-up of these people are independent from the exposure. You make sure they are exposed and unexposed, but you not measure them because they are exposed. Okay, with equal intensity in both groups to determine the disease status for each study subject. Source of confirming disease status, many. That's an easy one. Source of follow-up information. You need all the information to follow them up. There are many sources I'm giving to you here. Basic issues in methodology. You need to have sufficient variation. Well, let's say you're studying on your exposure. Let's say you study nutrition, relationship between nutrients and chronic disease. Historically, that is very difficult to find relationship. The relationships have been very small, like risk ratios 1.3, 1.1, 1.15, 1.4 maximum. 2, it's a rare thing. So when you have relationships between a nutrient, let's say percent fat in your diet, or vitamin A, or coenzyme A, whatever, okay, and heart disease. If you have a small group of people with variation, you're not going to have a large difference between exposed and unexposed group. So you want to select your exposed and exposed in such a way that you have variation. If your exposure is continuous, like those chemicals in your blood are, you want to make sure that you have a high range of patients with high variation. So why is my point? Why this is not somebody else? My point, and I know it's true, but the theory is strong on what I'm going to make the argument here. Why is nutrition epidemiology only giving you small relationships, 1.1, 1.2? Because diet in America, and that's 99% of the studies in nutrition, chronic disease, is very homogeneous. People eat the same SHIT, okay? And they eat a lot of fast food, a lot of sugar. The average consumption of ice cream in America is like 10 times of a European, whereas the European drinks 10 times what an American drinks. That's another. So anyhow, so homogeneous diet, everybody eats very similar. The very poor, the very rich eat the very bad food. There are exceptions. Therefore, you don't find much variation. Remember, you need contrast. You need exposed and unexposed. But if you're dealing with a continuous variable, and that's the nutrition, you don't have much variation. So you need to find areas of people that provide you variation in the exposure level. Must have adequate sample size. We're going to talk more about it tomorrow when we talk about trials and the importance of sampling for power, sizing your sampling population for power. Okay, but if you don't have enough observations to make your accurate statements or measurement of associations, you're not going to get anything that is important. That's another study. Again, all my diagrams are coming like that, the words, but you can figure exposed to silicon, unexposed silicon, connective tissue disease, not connective tissue disease, no participation, participation, eligible, ineligible, and so on and so forth. That's a nurse, very famous nurse study. So cohorts are very good to study rare diseases because you establish from the outcome exposed and unexposed. You measure the exposure. Now you follow up people over time, 1 year, 2 years, 3 years, 5 years. Some cohort lasted 10 years. Framingham is 60 years. But the first cut they did in 2 or 3 years, they're already doing studies, 5 years, 10 years, so on and so forth. Okay, and Haynes is a big population-based cohort done by the Centers for Disease Control and Prevention. You can use that data. It's publicly available to do cohort and the things they measure. The only weakness is that you cannot add new things. It's a retrospective cohort. They already done the follow-up, and you are using that data to do your retrospective analysis. But so cohorts are very good to study rare exposure. You can multiply effects of a single exposure. Like tobacco, you can create gradients. Never smoker, former smoker, smoker of 1 pack a day, more than 1 pack a day. So you have 5 levels. You can create 7 levels. And with that, you create something very important in epidemiology. You should know that from basic epidemiology, which is gradient. Once you have gradient of the association between the risk factor and the outcome, the treatment and the health outcome, then you have more evidence in favor that this relationship is actually causal. Because the little increase on this, the disease is increasing proportionally that way, as opposed to have just 2 levels of outcome and 2 levels of exposure, which it can establish just a relative risk, but you may miss information in the middle. So you can compute incidence rates for exposed and unexposed, very powerful measure. Incidence rates allow you to study more deeply association, including through survival analysis. We're going to mention just en passant about Cox model or any other type of survival analysis. You can use a Kaplan-Meier statistic to look into. Can establish time sequence between exposure and disease for sure. You know that exposure preceded the outcome. So you're never in doubt. In a case control, you may be in doubt. in a cross-section, for sure you doubt. You never know. There are some crazy exceptional cases, but usually cohort is the best observational design. Limitation, yeah, there's some limitation. If you're going to study a rare disease, following people up, you're going to wait for 2 lives for that event to happen, right? So it's not good for rare disease. It's not efficient. You're not going to study a rare disease with that. Because you don't establish the study group based on disease, you establish based on exposure, waiting for the disease to happen. If the disease is rare, it's not going to happen. And if it happens in small numbers, you can't study it. Example, why do you think we know a lot about the exposure association between lung cancer and many risk factors, including tobacco? Because it's the most common cancer for the past 150 years. It's lung cancer, followed by colorectal cancer. So it's easy to study when you have a lot of cases. Trying to find out what causes cancer of no, very actually has a little bit, but the conjunctive tissue or something like that. You know, cancers are very rare. For instance, we still don't know what caused thyroid cancer. We have supposition because it's very rare. It's 1 in 10,000. So you don't have enough to study. If you want to say, oh, I think it's radiation. So let's say expose these people to radiation. They've been exposed to a lot of radiation. Let's follow them up. You may wait 20 to 30 years. So rare disease cannot be studied with cohort study. It's not efficient time. Loss to follow-up affect validity hugely. So do not lose people to follow up. But again, you know, there's so much you can do. Make it enticing so they can be part of that cohort group. It can be expensive, time-consuming, absolutely. If I do a cross-sectional survey in America today, I can sample, I can sample 5,000 people for about $100,000. But if I do a study including 1,000 people and follow them up for 5 years, it's going to cost me $7 million, $5 to $7 million. That's a huge difference, right? 100,000 to 7 million, that's a lot. It's about 70 times more expensive, 70 times more expensive. So you don't do that. Strength and limitation, you can study that. There's a little bit of both the historic and perspective. The limitation of the historical is, you know, you have the data not usually available for potential confounding factor because there's already collected. It's not you who has collected the data. That's a big limitation. And it may be a unreliable exposure. To measure recurrence, like I said, the incidence rate and the risk. And then out of that, I can create incidence rate ratio, and risk odds ratio. So let's say incidence rate. Read this carefully later on. Incidence density data cohort. That's how I present the incidence rate correct. Everything is here in this diagram. You have exposed people in a column, first column. You have unexposed people. That's the people I'm following up. Let's say I have 100 people, and each one of these 100 gave me months of follow-up period. It's a 5-year study. I have 100 people. Some people gave me 100. Gave me 100 days. Some people gave me 30 days. Some people gave me, 60 days. Okay, something like that. I'm following them up over time. And then you have your personal time. We sum them up, calculate the incidence rate. A divided by PT1, that's the incidence rate for the exposed. B divided by PT2 is the incidence rate for the unexposed. Because I am doing a cohort study, I'm not interested in M1 divided by PT. Okay? So you have incidence rate in the exposed, incidence rate in the unexposed. If I divide the incidence rate for the exposed by the incidence rate for the unexposed, I am in a territory called incidence rate ratio. I sub E divided by I sub U. Incidence rate difference is when I take the incidence rate in the exposed and minus the incidence rate on the unexposed. That's the portion of the incidence attributed to the factor that I'm interested in, the exposure factor. I can then, with this, establish measure of association like I did here on the left, and I can do my hypothesis test. My hypothesis testing is that under HO, exposure is not associated with the outcome. The way to represent that easily is say, M1 estimates a random variable that follows a Poisson distribution whose parameter mu and variance mu equal to M1. I'm basically saying, the incidence rate I'm getting should be M1 over PT. That's the average incidence rate for both exposed and unexposed. If there's no association between exposure and the outcome, the A over PT1 and B over PT2 is going to be identical to M1 over PT. And PT is the summation of PT1 and PT2. So PT1 plus PT2 is total PT. A plus B is M1. So M1 divided by PT is the average rate for everybody. I'm saying, hey, there is a gradient here. Exposed group should have a higher incidence than the unexposed. And the null hypothesis say, no, it should be M1 over PT, which is the average across all groups combined. Okay? So here I'm giving a little bit of the theory. The A over PT1, it's a realization of M1, and A over PT1 is a realization of this. If I believe the Poisson distribution with parameter mu and variance mu. Okay? Just to remind you of the statistical foundation here. So the incidence rate ratio is the ratio of an incidence rate in the exposed divided by the unexposed. If it's 1, there's no association between the exposure and the outcome. If it's more than 1, the exposure caused the outcome, or it's influenced positively the outcome. That the more exposure, the more outcome. Detrimental effect. If the relative risk, incidence rate ratio, is less than 1, there's protective effect by the factor that I'm interested in. I can actually estimate a incidence rate like I did. One notation is this one, A over PT1, but the other notation, very common in many books, is A1 over T1 divided by A0 sub 0 divided by T sub 0. That's the same thing. The incidence rate in exposed divided by incidence rate in unexposed. And the standard deviation of that to calculate the confidence interval is very simple, actually. It's 1 over A1 over 1 over A plus 1 over B from that diagram before. And I take the square root of this quantity. That's the standard deviation of the log of the incidence rate. Because it's a standard deviation of the log of the incidence rate, if I exponentiate this back, I bring it back to normal, right? And that's what I do here in a 95% confidence interval around the incidence rate. I exponentiate the log of the incidence rate plus or minus z, that's 1.96 for alpha of 0.05. So I calculate the 95% confidence interval and then multiply by the log of the IR. And the whole quantity is exponentiated, the log of the IR plus or minus z that multiplies standard deviation of the log of the IR. Once I have that quantity exponentiate that, I got the 95% confidence interval. Okay, here's an example of ART, which is the famous treatment for tuberculosis. And there are personal years of, that's a big study on ART back in the time in the 80s when you're still debating whether you should do ART or not. As you all remember, ART is the treatment that you basically observe the patient takes the medication. The medications for tuberculosis are so toxic, most patients start refusing after a few weeks, but they need to take this medication for months to be cured. So you need to observe them taking the medication every day. That's ART. So you have a group of people who gave 1,661 person years of follow-up. The other group, the unexposed group, gave 1,641, very similar person times. Then you have 17 people developed diabetes in this group and 33 in the non-exposed to ARTR. And the incidence rate on one group is 0.01, the other one is 0.02. So you know the incidence rate ratio is going to be equal to 2. Okay? And that's how we calculate that value of 2 in the confidence interval. Sorry, the unexposed to the exposed is 2, but the exposed to unexposed is half of that, which is 0.5. Okay? So that you know that the ART protects against development of tuberculosis, or it does cause the tuberculosis to disappear in somebody's body after you do an ART the right way. Okay, and that's up at about half of the other group, the unexposed. And the confidence intervals goes from 0.28 to 0.91, and the average measure is IRR of 0.5. So I'm going fast because you can read this. I put all the formula, all the calculation here. You can look it up. You got the rate difference, same idea. Read about it. I'm going to go quick. What time is it, Fred?
11:10.
Okay, we're near close to time. I need a ton of 10 minutes with you. No, I need to cover another thing later on. No. Para segunda aula, Luis. I'm already have this. This is a second lecture. I need to give 3 lectures. I need to finish that now. So the other way to present cohort data is the count data. It creates another measure of association, the relative risk. You have that famous one I showed early on. A, B, C, D, M1, M2, N1, N2. So you have N1 exposed people followed up over time. See how many developed the disease, how many A are the new cases of the disease, and B are the new cases of the disease in the unexposed N2 group. And you can calculate the rate, the risk in one group divided by the risk in the other group. That's a risk ratio. And the risk difference is the risk in the exposed minus the risk in the exposed. That's your attributable difference. The portion of the risk attributed to the exposure to the risk factor. Again, you do the same trick. RR greater than 1 is evidence that the exposure increased the incidence, a detrimental effect. On RR or less than 1 is protective effect, meaning exposed to that factor diminish the incidence over time. Risk difference, same idea. Here, the confidence interval for the incidence ratio, the cumulative incidence ratio, the risk ratio. That's the risk ratio. It's very easy formula to understand. If you plug, instead of A, B, C, D, you say X1, N1 minus X1. It could be A or N1 minus A. Okay? It could be something like that. Or B, N1 minus B, whatever nomenclature you want to use. You have, point is you have N1 exposed people, N2 unexposed people. This is the confidence interval. You see how easy it is to calculate that? This quantity here is a measure of the dispersion or the variance of that risk. Okay, it's the weighted jointly variance of each individual risk. Okay, and you take the square root that, you got the standard deviation multiplied by Z, but they're all in a so-called logarithm, natural logarithm scale. And you need to exponentiate back to bring them to life. Sorry, folks, I feel bad about it somehow. Okay, so you compute the confidence interval of the log of R first, and then you exponentiate back to bring back to normality, to RR. And the reason I didn't explain to you, but the reason take the logarithm of relative risk or incidence rate ratio, and you're going to do the same later on odds ratio for case control, is because the distribution, the frequency distribution, all possible incidence rate ratio, all possible risk ratios, they are a curvilinear skewed to the right. And when you take the logarithm of that, you bring it to normality because you need to use the Z. A Z is the standardized normal. It's a bell-shaped curve. But the curve that you actually have for the all possible RR, all possible IRR, all possible odds ratio you're going to see later on, they're skewed to the right. They're kind of a gamma distribution. If you have a gamma distribution, you take the logarithm, every value, that gamma distribution becomes a normalized distribution. You could bring them to the center. That's why you're doing this, folks. So you can apply the law of large numbers, the approximation of the confidence interval of a variable that's actually in a binomial territory. You could use the binomial distribution to come up with an exact confidence interval. But I'm doing an approximate confidence interval based on the approximation to normality because most cohort studies are done with more than 100 people. You usually have more than 100 in each group to follow people up. So you're in a territory of normalized type of values. As you remember, as n becomes bigger, the binomial approximate what? A normal distribution. As n becomes bigger, the Poisson approximate the binomial, and then if you're larger, approximate a normal distribution in terms of the parameters you want to estimate, not the value of the original variable itself. More talk for your statistics course. Here, how to calculate. I gave you the formula here, and I give you a real calculation with real number. Okay? You can follow this up, no problem, except that the graphs are, I'm sorry, folks. Fred, can you do some trick later on and make sure
Yeah, yeah.
when you fix them so when they copy, okay? So here, therefore, you can have a calculation, you can know how to calculate that. I want you to study that, okay? Remember that formula I gave it to you here? N1 minus X1, X1, I did it in a different notation, B over A plus B. It's the same thing, okay? Another example, so I gave you 2 examples here. So with that, I'm going to quickly say there's something called risk-odds ratio. I will cover that in the next few minutes before we go to case control. I'll give 10 minutes on the risk-odds ratio from the cohort. Take a break of 10 minutes. We'll come back 10 minutes. We do a 40 minutes lecture on case control with 5 to 10 minutes on risk-odds ratio from cohort. Go, folks. Take a 10 minutes break, folks. Anything longer than an hour and 50 minutes is difficult for people to pay attention. That's why you need to break.
Eu fico lá reunindo até a hora que vocês chegarem.
Sexta a gente saiu no censura.
pessoal, tem outra medida importante. Em português, não, it's English. The course is supposed to be in English, being recorded. Okay. There's another important measure in a cohort study. That's a risk-odds ratio. It is important theoretically because you need to understand that measurement to understand why you have an odds ratio in a case control. Why it's not that important in the cohort itself, a risk-odds ratio? Because I have the relative risk. I have the incidence rate ratio. They are the fundamental measures. Risk-odds ratio is a indirect way to measure a relative risk or risk ratio. Okay, remember that. The risk-odds ratio is an indirect way to measure the relative risk. Why? Because the risk-odds ratio is nothing more than the odds of disease among the exposed divided by the odds of disease among the unexposed. We're going to see that. If the risk-odds ratio is equal to 1, there's no association between the exposure and the disease. If the risk-odds ratio is greater than 1, like the relative risk or the incidence rate ratio, there is an increased risk of developed disease among exposed compared to unexposed. And if the relative risk-odds ratio is less than 1, is equivalent to a risk ratio less than 1, there is a protective effect of exposure on the incidence or the risk of the disease. So it's an estimate of the relative risk. Usually when the disease is rare, depending on the design of your cohort study, which is usually good, you can make some generalization and accept, even when it's not so rare, the outcome of your interest. I'm not going to get into that math. It's very complicated statistics, and it's not the focus of our analysis and discussions today. So in this situation, when the outcome is rare, or disease in this case, the number of cases M1 is very small relative to the total number of known cases, which is going to be very close to the number of total population, meaning the M2 group, the unexposed, it's going to be the non-disease group and the exposed very, very similar to the total population. Okay, so when you have situations like that, you can estimate the relative risk by the risk-odds ratio. And that's what I'm saying here. So you remember that A, B, C, D. If C becomes very close to N1 and D very close to N2, then A over B divided by C over D approximate A over N1 divided by B N2. So let me repeat again. The risk ratio is the risk in the exposed divided by the risk in the unexposed. And that's A over N1. The risk in the unexposed is B divided by N2. So one risk divided by the other is a risk ratio. The risk-odds ratio is the odds of exposure, odds of disease among the exposed, and the odds of disease among the unexposed. It's always easier to get carried away and think about a case control, which is different. Similar idea, but different. So we end up with A over B, C over D. I hope I have yes, I do have a graph. Okay. No. Where's the graph? With A over B over D. Sorry, folks, I'm going to go back. Okay. So here, if you say A over N1 is your risk of becoming a new case over time, or risk of disease developed over time among N1 exposed people. B is over N2 is the risk of disease among N2 unexposed people. You follow that, right? So what's the odds that you're looking at here? In a case control, you're going to see later on, I have diseased people and I'm looking at the odds of exposure. Here I have a cohort. I have exposed people. I look at the odds of disease. So what's the odds of disease in the exposed group? Exposed group is A, C, and N1. So what's the odds? The odds in the exposed is A divided by N1 divided by C that divides the N1. So it's the ratio of the A over N1 by C over N1. Well, the denominator is the same. They cancel out to become A divided by C. And that's why people in their betting in Las Vegas or any kind of racing, like horse racing, they say it's 2-to-1, 3-to-1. Okay? Let's say you had a 4 here and you have a 2 in A and a 2 in C. So it's 2 divided by 4, 2 divided by 4. So the 4 cancel out arithmetically, you end up with 2 over 2. So the odds here is 1. It's 2 to 2. Okay? It's an equal odd. So that's the whole idea of odds. And if I divide that odds by the odds in the unexposed group, I get the odds of disease of the exposed divided by the odds of disease unexposed. And that's what I'm talking about here. Sorry for not showing that drawing again here. Okay? So you end up with, if C is very close to N1, remember A, B, C, D, if C is very close to N1, then divided, creating the odds A over C becomes very similar to relative risk. To risk is like C over N1 and D over N2, okay? So that's how you end up with a odds ratio that's very close to a risk ratio. Here's an example. I have a large number of people being followed up, and the event is rare, 378 myocardial infarction out of 20,000 people, more or less. So the odds of a myocardial infarction among the aspirin user group is 139 divided by 11,037. The odds of MI placebo is this much here. It's like the risk, okay? So the two odds, formula, the first, not formula one, the race, but the first formula. The odds ratio is the ratio of the two odds. You end up with these values, 0.576. Let's say I want to estimate the risk ratio. The risk ratio would be 139 divided by 11,000 and divided by 239 divided by 11,000. It's going to give a number very similar to 0.576. But here, what I had was the odds ratio, which is 139 divided by 10,898 and 239 divided by 10,795. Okay, that gives me those two numbers here. And if I take the ratio of these two odds, 0.013 and 0.022, you end up with 0.576, which is very similar to the risk in the aspirin group, the risk of myocardial infarction in the aspirin group divided by the risk in the placebo group. Okay, here's the formula for the confidence interval of the odds ratio, risk odds ratio, 1 over A, 1 over B, 1 over C, 1 over D, and square root of the whole quantity. You know this is the variance and the standard deviation of the log of the odds. And then you have to exponentiate later on to bring back to normality, as you see here in the latter part of the drawing. Okay? So I'm not going to mention that. Read about survival. It's just a measurement. We're going to jump into another lecture of case control to finish the day on the two more important observational design that you need to understand to evaluate interventions in the future, because they go very often in the so-called natural experiments. Okay, we're going to talk now about case control study. So in a case control, we're interested in odds ratios too. A measure of association is the exposure odds ratio. It's a reverse mirror of the risk odds ratio. It's a risk odds ratio for the case control. The theory behind it is the same and was proven by a great many medical statisticians in the past based on the Bayes theory. You can prove and show that the odds ratio for the cohort is identical to the odds ratio of the case control in terms of mathematics and statistics. In orientation is different, but they end up being the same thing. So you start with the disease group and the non-disease group, and you go back for exposure. It looks like a retrospective cohort, but not. In a retrospective cohort, I go back in exposure to establish the exposed and unexposed group, and I prospectively follow them up for disease occurrence. Here, I have the disease already occur. The disease occur already. The non-disease group is just the control group for that case series, and I'm going back to trying to find the exposure in these people. I go backward in time. Here you have, again, ineligible, eligible, participant, non-participant, bad outcome. I follow them up over time. Bad outcome, good outcomes. And then I go back and say, hey, of the bad outcome people that are following them up over time, theoretically, this is what I found in the past. They are exposed, unexposed, exposed, unexposed. Fred, you fixed that, right? So case definition, clear, standardized, and discriminating definition of a case. Define the specific disease of interest, define the source of that population, define the eligibility to be in a study. And you create exclusion to maximize the findings of your odds ratio later on and to maximize the absence of bias. So you don't want to include people that should not be in that study. Those who are the known causes of your disease that could affect, you eliminate there if you want to. You don't need to adjust later on for confounding. You may eliminate some tough to measure confounders right there at the exclusion level. Inclusion criteria, you should, example of inclusion criteria, I gave a crazy example here of a child diagnosed with non-syndromic cleft lip or palate at the cleft. So the idea here is to study on cases of oral cleft versus controls who don't have oral cleft and to find out what causes it. Okay, so that's what the original study. And then you have your definition, see how clear the inclusion criteria is, and the exclusion, you exclude child diagnosed with cleft palate only or a typical cleft. You want to study just the typical cleft. Child diagnosed with a syndrome, it's a syndrome, it's not specifically that condition. Biological matter is not present. You cannot do it. Extrapolation of confounding variables from parents' interview on the child issues. Biological matter does not speak Thai or Insan. That was done in Thailand. Here's the paper. You can look it up for that case control. But a clear inclusion-exclusion criteria to eliminate the possibility of invalidating the study for difficulty of implementing, like biological matter is not present, biological matter does not speak, or getting confused what the actual case is. So you eliminate those things that could be falsified, a real known case with a different genetic possibility. Mirror case definition. The control group has to mirror the case definition, but does not have the disease. So they need to be the very same person that could have been a case. You want to make sure they are the same. So how do you do that? They come from the same source population. You have the same eligibility criteria applied, the same exclusion criteria. You end up with people who are likely could have been case if they're not your control. They must fulfill the same eligibility criteria defined before. Okay, we already mentioned that. This is an example. For cervical cancer, over 50 old women more. If the case are women with cervical cancer over 50 and more, the control must be selected from the women in the same age group, because you may be then comparing. Let's say your study is on cervical cancer. Let's say in 1965, you're in a city where I was born, Recife, northeast of Brazil. They had at that point the highest rate of cervical cancer in the world. Okay, so you wanted to study what caused cervical cancer in 1958. So you do study and you have a bunch of women over 50 with that. Do you want to include women at age 18? No, their habits are very different. What if the cause of that disease is related to a behavioral thing? You know that women over 50 are very different in behavior from women of age 18. For example, now later on we learn that cervical cancer, the main cause of cervical cancer is actually infection. And the infection is a sexually transmitted disease. It's a virus. Okay, the herpes virus, you know, that, or the family of herpes virus could cause cervical cancer. And you have now vaccine for one of them. But at that point in time, you're still studying. So if you included 18-year-old women, we never found out, because their sexual behavior very different at age 15 and age 18. So again, you want to make them comparable. They could have been cases if they're not controlled. The same cleft palate idea before. So you study, read it, ask me a question. Okay, select population of case, use historical data is problematic, but that's the only way in most case control study. Exposure level of exposure measurement results compare retrospective between case control to test a priori hypothesis. That's usually the case in a case control. You are usually having a retrospective data collect on both the exposure levels for both case and control. Criteria for selecting cases, again, should represent homogeneous group. Use incident case. Do not do case control with prevalent cases. Make sure there are incident cases. Otherwise, you're not replicating in a quick and dirty way a cohort study. You're representing something else. You need to have incident cases. Okay, it avoids a lot of bias, especially selection bias and confounding of all types. Criteria for selecting case are banned, ideally trying to do live cases versus not a live case. Even though I'm going to show an example on Friday to you of that case control of dead people. Vital records, source of data, population-based, medical record. You can identify cases based on that. Usually, the easiest way to find cases for case control is hospital-based cases. But then you're almost forced to have hospital-based control, which are not too good, right? For practical purposes, it's good, but why is not a control for hospital a good thing? You want to make sure controlling cases come from the original population where cases come from. So that check, that's true for the controls from the hospital for a case that came from hospital. But you got another problem. The problem is the person's in the hospital for a reason. Even though they don't have that specific disease you're interested in, they are not case, but they're case of something else. And disease in general, disease people have something common. So there's going to be difficult for you to disentangle the selection bias and the confounding bias. Study that lecture on selection and confounding, okay? Selection bias and confounding. So you don't want to control from hospital. You want to control from the general population that gave rise to the case. You want to control from the population in general. Ideally, you take a random sample of the population surrounding the hospital or the catchment population of the hospital, okay? Should be selected from the same population. Again, that's the example, should not exceed. Another thing, people say, I'm going to do a matching case control, matching case to control to eliminate confounding bias. You learned that in that lecture. I gave it to you that I did not present, but you want to study early this morning. You want to go no more than 4 controls per case. I don't have the time to show, but mathematically it's a waste of time. I see many papers published, 5, 7 control per case. You're gaining nothing. You're just wasting money and time and energy, okay? It's maximum 4. Most purpose, 2 to 1 does the job. 3 to 1 is excellent. 4 to 1 is the maximum should have, maybe for power. If your number of cases are too small, you're still going to have problem. You need to have a reasonable number. We're not going to get into that discussion of power for case control. But again, consider the fact that you don't need more than 4 controls per case. More on selecting control. You want to match them. That's a good idea. But also the way you sample, you bring controls into group, it may bias your study, meaning the select should not be more or less likely if they have exposed or not to a risk factor that you are interested in. You need to make sure they are independent from the exposures, that you're trying to understand the relationship between that exposure and the outcome. And ideally, they should come from the general population that gave rise to the cases. Many options here I'm giving to you. Again, more options for controls. Criteria for access to exposure. More important point I make here is must be collected from the period prior to disease development. You want to make sure that the exposure preceded the outcomes. You don't want to confuse when the exposure happened, like in a cross-sectional or prevalence study or a survey study. You don't know what comes first. There are exceptions to that rule, but usually you don't. So you want to make sure you have incident cases and you preceded the cases with exposure information. Exposure preceded the development of become an incident case. Source for identifying and assessing exposure menus, I'm giving to you, read about it. So what's the basic methodological issues? There are many. Sample size to minimize rule of chance. Very important. We're not going to have time to cover this in this lecture. It's a review lecture. But to maximize precision, you need to make sure you have enough cases, enough controls. And like I said, 4 to 1 is the maximum you should have for 4 controls to 1 case. Ideally, 2 to 1 does the job well. You don't need more than that. 3 to 1 is exceptional. 4 to 1 is super exceptional. You minimize bias in selection of case control. The selection of your case series and your control series have to be independent. Also independent from the exposures. So in that way, you prevent selection bias to creep in your study. Fred will fix that again. This is an example on cancer smoking. The null hypothesis of lung cancer rate for smokers is the same as lung cancer rate for non-smoker. Your alternative hypothesis is that they're not the same. It's not a watch. It's not a clock. It should be a sign of different sign there. Here you have your traditional, very similar to the cohort presentation for count data for relative risk or risk ratio or risk odds ratio. You have your exposed group and exposed, but more importantly, the case control, you start with A plus B cases and C plus D controls. Whereas in a cohort, you start with A plus C exposed and B plus D unexposed. Okay? So in here, you can calculate the odds of exposure. What's the odds of exposure among cases? What's the odds of exposure among the cases? It's A over A plus B divided by B divided by A plus B. The A plus B cancel out, becomes A plus B. And the odds of exposure among the control group is C divided by C plus D divided by D divided by C plus D. You end up with C over D. And now if you take these two odds, divide one by D, you end up with A, D, B, C. A that multiplies D divided by B that multiplies C. It's the same odds ratios you had in a cohort study, except that one is called risk odds ratio. This one is called exposure odds ratio. Okay? Here you have the writing on the right-hand side here. You can see how that they fall off. So disease risk or rate cannot be computed directly from the case control, because disease risk among the exposed should have been A divided by A plus C, but your A plus C is not the true A plus C. It's a representation of that, a subset of that. You don't know if that subset, the A plus C proportions are identical to the original population. You have no, so the red here means I don't know what the true A plus C is and the true B plus D. I have some other numbers there because you don't know the true exposed and unexposed subjects. Okay? We have only cases in control. That's what you do. We can certainly calculate the proportion of exposure for case of control, and that's the odds. Okay? So you're actually doing the odds of exposure among the cases. You say, given an arm case, what's the chance I am exposed? That's what you're doing. Okay? So that's your odds of exposure, A plus divided by B. And the odds of unexposure, of the exposure among the control is C divided plus D. So that's your other odds. You divide one by the other, you got the A, D, B, C. Again, the exposure odds ratio, which is calling odds ratio at this point, if it's equal to 1, there's no association between the exposure to the risk factor and the outcome. If it's greater than 1, then you have indication that the exposure to that factor is associated with an increased chance of being classified as diseased. If it's the reverse, you have less of a chance. Okay? Hypothesis tests for odds ratio and relative risk are not used to determine statistical significance of the association. Instead, confidence interval. What I mean by saying that you can do statistical testing, but you have something better. You have your confidence intervals around the ratios or the risk, relative risk, or whatever. In both cohort and case control, use them. Because it gives you not only indirect measure of the statistical test of measure of association, but also gives you the value of the measure of association and the spread, how confident you are that the true value lies in between what and what. That's your confidence interval. Here's an example, exposure odds ratio. So the other question you have in case control is that a good estimation, my odds ratio of the relative risk? You know that the exposure odds ratio is not the risk odds ratio, but the exposure odds ratio is an estimator of the risk odds ratio. And here I'm showing the risk odds ratio again. So you can see that the relative risk and risk odds ratio are very similar, especially when you have the numbers are approximating each other. Okay, when your small number of cases, you have a problem. When you have large numbers in rare disease, when the disease is rare among the exposed group, B becomes almost the same as A plus B. When the disease is rare, in general, the D becomes very similar to C plus D. Okay, so if I do A divided by B, it's the same as doing A divided by A plus B. A divided by B is the odds of disease among the exposed. Okay, And A divided by A plus B is the risk. This is a cohort table, folks. See the name here. Look at the cells from cohort study. So they become the same. So if I do the odds ratio, risk odds ratio in this case, and the risk ratio or relative risk, is going to give similar numbers. Okay? Especially with the disease is rare. I'm basically saying if I have 1,000 A plus B people is 1,000. And I have, 50 cases. So I have 950 no cases exposed. So if I divide A by 1,000, and it's going to be very similar to A divided by B, which is 950. So it's 50 divided by 950 or 50 divided by 1,000. It's going to give similar numbers. You end up with two the same. So both are similar, okay? And you can get that also for exposure odds ratios can give you that. I'm not going to prove it to you, but by Bayes' theorem, I showed that in a very first lecture I gave you yesterday. There's a lot of note that shows by Bayes' theorem how the risk odds ratio is the same as the exposure odds ratio. And here I have a different scenario, still in a risk odds ratio, showing the numbers to you, how they come about. The risk odds ratio and the relative risk are very similar numbers, 258, 243, okay? It's very similar. And then I'm going to show you that in a case control, this number is going to be very similar too, okay? Between the theoretical risk odds ratio and exposure odds ratio. So indirectly, the exposure odds ratio is a good estimator of the risk odds ratio. And therefore, they are good, both are good estimator of the relative risk. You can read this, study it. Fred, how's it my time here?
It's 8 to 12.
8 to 12.
8 minutes.
Yeah, we have about 10 minutes, folks. So odds ratio and confidence interval, you know how to calculate. Why we calculate an odds ratio? Because you cannot measure relative risk or incidence rate ratio in a case control, but you can measure the exposure. And among the disease and exposure among the non-disease. So you calculate the odds of exposure among disease divided by the odds of exposure among the non-disease. And you take the ratio of these two, end up with the exposure odds ratio, which is an estimator of the risk odds ratio in a cohort, the original cohort, which estimates the relative risk. So indirectly, you are estimating the relative risk. Yes, there is error between the exposure odds ratio and the true relative risk. But usually, given some circumstances, this difference is very small. Especially, I didn't have the time to go over with you. It's not a lecture on case control. I have 5 lectures on case control to show the different types of designing a case control that allows a case control to become closer and closer to a cohort study. The way you select your sample, the cases and control make a huge difference in the way you measure the exposure. It allows you to get almost certainty that your exposure odds ratio are identical to the risk ratio. Here, I'm going to show you, again, the same trick of the natural log, because they need to scale in a different way, because the original distribution of the so-called exposure odds ratio is skewed to the right. That's the frequency distribution of all possible exposure odds ratio. If I could repeat similar studies to the one I have at hand, if I could repeat that study 100 or more times or infinitely, I would have distribution of all possible exposure odds ratios for that association between that risk factor and that outcome. So in that theoretical distribution, there's a curve, and that curve is curved to the right. It's skewed to the right. If I take the logarithm of that, it brings back to a bell-shaped normalized curve. So risk ratio works like that, risk odds ratio and exposure odds ratio. So I calculate the confidence interval in the logarithmic scale, the natural logarithmic scale, and then I scale back by taking the exponentiation of that, because the exponential, EXP in Excel or programming language, is the inverse of the ln, the natural log, okay? So I'm going to show you the formula. You got the formula, very similar to the one in risk odds ratio, the same formula. That's the 1 over A, 1 over B, 1 over C, 1 over D. That's the variance of the odds ratio. The square root of that is standard deviation of that variance both on the logarithmic scale. So that's your standard deviation of the log of the odds ratio, okay? Once you have that, you know that you can multiply that by 196. You have the plus or minus boundaries of your confidence interval around the logarithm of the odds ratio. Okay, here an example. I did the calculations for you here. You can see how that goes through. And I'm promoting that you use confidence interval as much as you can and don't rely so much on a test statistic because it has more information. You now know that the odds ratio here, whatever value you have, has a boundary between 7.6 and 13.1. Well, the odds ratio, in this case, exposure odds ratio was 10. So now the truth lies in between 7.6 to 13.1. If I rounded to no decimal, it would be like 8 to 13. So you know that the most likely value is 10, but very strong possibility of being between 8 and 13. That's a good information. So you have no doubt that these are strongly associated, this risk factor, fake one that I created here, and this fake disease, they are highly associated. Okay? Another reason I did this crazy example here is because remember they say rare, when the disease is rare and a case controlled, the exposure odds rate approximate a risk odds ratio and therefore approximate a relative risk or risk ratio. Here, I did not make the disease to be rare. I be it to be very common, but their measure of association is very strong. And the point here is to make is that the exposure odds rate on its own is a measure of association, even if it's not measuring indirectly the relative risk, which is a secondary interest. Okay? Here, likely, it's not a good measure of the relative risk, but it's a measure of association. A number big like that with a confidence interval like that cannot be explained by biases because of selection or confounding, unless it's a huge selection bias, very obvious. And that study, that is a fake study, that you would see it clearly from the beginning. You never allowed that to happen if you're a good epidemiologist. So therefore, you have more information on a confidence interval than just a simple statistical testing. So use the confidence interval. Another example here on another study, and I just give you the numbers so you can calculate yourself. Okay? Read over, send me questions by email. Fred's going to give you my email. Yesterday, there's only 2 questions from the live, no questions by email. Feel free to send me requests for questions. I'll answer them as they come along, okay? By the end of the day, remember the limitations of the cohort was that I cannot study rare disease. Here, the main limitation, it's inefficient to start rare exposure because I'm not going to find them, right? So I have my case, but then I'm interested in an exposure that doesn't exist. And most of the cases that I identify, I'm doomed. I cannot do a cross-tabulation between exposed and unexposed and case and control. So it's not good to start rare exposure. And assessing exposure from the past may be problematic. I may have problem. And sometimes, depending how I define my case, I have problem in temporal relationship, meaning establishing that the exposure of that individual to the risk factor preceded the development of the outcome of my interest in the study. If that's the case, I'm doomed. I cannot have a good study, but it's tough in a case control sometimes to do that. So it's most susceptible to certain types of bias, especially selection bias and confounding. Okay, folks. I think I did, it's still in the realm of reviews. I think what's going to be new to you is the lecture starting tomorrow, and then Thursday, and then Tuesday, and the one on Wednesday. They're very much what I call innovative for a lot of what I expect to hear. And like I said in the beginning, the gist of this training is to allow you to feel more confident and competent to evaluate interventions, population-based intervention, clinical interventions, clinical trials. Feel more confident. And tomorrow we're going to dedicate a lot of time to clinical trial. The whole 3 hours is going to be about clinical trials. I'll bring about one level of clinical trial, the other level, which is very important for evaluating large-scale intervention in a population. That's going to be taught next Tuesday, okay? But tomorrow is the beginning of that. So you'll be a great audience because not many of you are here and you're not asking too many questions live. Therefore, I'm not interrupted and I'm talking a lot. Appreciate that. Is that 12 o'clock?
Yeah.
Okay. I'm going to finish on time so you can have your rest of the day free. You can eat your great lunch. You'll be a wonderful audience. Thank you. Have a good one, folks.
Thank you.
Thank you. Fred, you can. Yep. Bonnie, I'm not